Hello everyone, thanks for tuning in. I'm Muhammadeziz Tursunniyaz and I'm a graduate student from UW Madison. Today, I'm going to present a paper about printed capacitive immunoassay for detecting SARS-CoV-2 viral particles. So as we all know, COVID-19 pandemic has cost many lives and caused unmeasurable socioeconomic losses around the globe. One of the important lessons we learned from this pandemic is that in order to control the pandemic on its early stage, we need to have access to sensitive, reliable, low-cost diagnostic tools. So our aim is to develop a printed capacitive immunoassay which is sensitive, reliable, and low-cost and suitable for large-scale fabrication. And also, we want to integrate our immunoassay with mobile healthcare devices so that people can test themselves at home and read the test results from their phone, and even they can send the results to their uh, healthcare providers to get some medical help. So here are the experimental steps. So first, in order to fabricate the sensor, we choose Kapton film as a substrate and clean the Kapton film with IPA and DI water to remove any chemical contaminants and dusts. Then we inkjet print the coplanar electrodes on Kapton film with commercial inkjet printer, and we use the commercially available silver nanoparticle ink to deposit the conductive traces. After that, we put the burnt electrodes inside an oven and bake them at 250 Celsius degrees for around 10 minutes. After that, we spin coat PVDF onto the electrodes to provide a three-dimensional immobilization layer for antibodies. And we also attached a custom-made PDMS gaskets around the electrode areas to form incubation wells. So we performed some characterizations about on our sensors. So first we look first we did some optical microscope imaging. So we looked at the coplanar electrodes on the left picture here. So we can clearly see the gaps, and the gaps is around 200 micrometer wide. And we also looked at the sensors spin coated to the PVDF film under the scan electron microscopy, and we can clearly see the porous structure of the PVDF. So to biofunctionalize our sensors, we incubate electrodes with 400 microliter of captured antibody for overnight. So the concentration of the antibody solution is 4 microgram per milliliter. And then we washed 3 times to remove any unbounded antibodies. And then we incubate the electrodes with 400 microliter of 1% BSA to block any uncovered spaces. And then we washed 3 times to remove any unbounded BSAs. And um, so here is the photo of the electrodes we used for these experiments. And in order to make sure that we actually have antibodies immobilized on, on the PVDF film, we we did an fluorescent imaging. So basically, we uh, incubate the PVDF film with Elixaflor 488 conjugated antibody, and so from the fluorescent image, we can see that definitely they are antibodies immobilized. So here's a very brief theory of operation. So now our sensors are functionalized with captured antibodies and blocked with BSAs to prevent any um, antibody falling. So we perform electrical measurements to record the initial capacitance of the sensor, and then we divide our sensors into two groups. So for the control group, we incubate the sensors with 200 microliter of uh, gold nanoparticle conjugate detection antibody and with 200 microliter of PBS. And since we do not have an antigen here, so we should not have any antibody antigen um, sandwich structure around the electrode. So if we perform a washing step, all the detection antibodies should be washed out. Then we dry our dry the sensors under the vacuum for around 30 minutes, and then we perform another electrical measurements to record the capacitance change. For the sample group, we incubate our the sensors with a gold nanoparticle conjugate detection antibody with antigen. So since now we have antigen, so we should have an antibody antigen sandwich structure around the electrodes. So if we uh, wash away any unbound antibodies, we still have this sandwich structure. So now we can perform another electrical measurements to uh, record the capacitance change. So here also we use gold nanoparticles conjugated with detection antibody. So the reason is gold nanoparticle can perturb the fringing field and alter electrode capacitance, so which can increase the sensitivity of our sensor. So here are the measurement results. So we measured 3 samples and 3 controls, and for each of them we measured 3 times, and we averaged the capacitances, and we observe a positive capacitance change for sample and a negative capacitance change for control, which is uh, agree with our hypothesis. Here we can also observe the gold nanoparticles under SEM, so it can help us to improve the sensitivity of our system. Conclusion, we demonstrated a low-cost electronic assay for detecting COVID-19, and our measurement results show statistically significant difference between sample and control. And of course, our sensor needs further investigation with patient samples. For next steps, we are planning to investigate assay sensitivity and specificity, and we also plan to experiment with patient samples to see how the sensor uh, perform in a realistic testing environment, and we will experiment with expanding the applications of the sensor to other infectious disease detection, such as detecting HIV and Ebola. Of course, for this, we need to functionalize our electrodes with antibodies specific to this disease. And finally, we want to integrate our assays with mobile healthcare system so that anyone who has access to a mobile phone can test himself or herself and read the testing results from their phone. So I will stop here, and I am uh, happy to answer your questions. And of course, you can, if you have any questions, you can email us to me or my advisor through this email address here. And hopefully, if you can join us on a live QA session, we can have a discussions. Thank you.